All right, let's dive right in. Today, we're going to get inside the head of one of the greats, Richard Feynman, to really wrap our minds around one of the most powerful ideas in all of science, probability. We're going to see how this thing we use for, card games and weather forecasts is actually the fundamental logic of the entire universe. So, let's start with the big one. What is the true logic of this world? I mean, really think about that. When you strip everything else away, what are the basic rules that make the universe tick? Is it some kind of perfect deterministic clockwork where everything is predictable? Or is it something else entirely? Well, the legendary physicist James Clerk Maxwell, the guy who unified electricity and magnetism, he had an answer. And it's an answer Feynman loved. He said the true logic of this world is in the calculus of probabilities. He's saying that chance isn't just a sideshow, it's the main event. It's the operating system for reality. Okay, so let's start with something we all kind of get. Let's begin with the everyday idea of chance and see how Feynman turns it into a precision instrument. Why do we even need probability in the first place? Well, it's because we're almost never working with all the facts. We're constantly making guesses. Is it going to rain? Should I bet on this hand? And for Feynman, this is the whole point. Probability isn't just some abstract math. It's a system, a tool, for making the best possible guess you can with the information you have. And this is where it gets really interesting, and how Feynman actually defines probability. See, for him, it's not some cosmic truth written in stone. It's our estimate. It's our best guess about what would happen if we could run an experiment over and over in our heads. And that means something huge. Probability is subjective. It depends on what we know. And if we learn something new, the probability actually changes.
Okay, so that leads us to a really crucial idea. The gap between what we expect to happen based on probability and what actually happens when the rubber meets the road. Let's see how this plays out. So get this, Feynman's team actually did the work. They flipped a coin 30 times, and they did that whole process 100 times over. Now you'd expect about 15 heads each time, right? 50-50. But look at the actual results. The first trial, they get 11 heads. The second, 11 again. Then 16, we don't even hit our expected 15 until the fourth try. The real world is messy.
And this chart is just fantastic. It shows the results from all 100 games. We all would have bet that the bar for 15 heads would be the tallest, but look, it's not. Getting 16 or 17 heads actually happened more often. Feynman has a name for this: fluctuation. It's the totally normal random noise you get in the real world. It doesn't mean your theory is wrong, it's just what chance looks like up close.
But, and this is the magic part, look what happens when you zoom out. Over all 100 games, that's 3,000 total coin tosses, and the fraction of heads they got? 0.498. I mean, that is just ridiculously close to the perfect 0.5 we expected from the start. Over the long haul, reality snaps right into line with probability. It works.
So, if a single coin toss is one random event, what happens when you start stringing them together one after another? Well, that brings us to this incredibly powerful idea called the random walk. It's a way to model how things spread out in a world that's run by chance. So, picture this. Someone's standing on a line. They flip a coin. Heads, they take a step forward. Tails, they take a step back. And they just keep doing that over and over. Now, on average, they're not really going anywhere, right? Because they're just as likely to go forward as back. But they're obviously not just standing still. So the question is, how far from the starting line do they typically end up?
And the answer is just so beautiful and simple. The typical distance they end up from the start is the square root of the number of steps they took. Not the number of steps, the square root. So after 100 steps, you're probably only about 10 steps away. After 10,000 steps, you're still only about 100 steps away. It's this incredibly neat formula that gives us a predictable number for a completely random process.
Now, this whole random walk idea isn't just for one person taking steps. Imagine millions of little walkers, like molecules of smoke in the air. All of their individual, random jiggling adds up to create a predictable wave of probability, a process we see happening all around us: diffusion.
Let's say we release a little puff of gas into a room. Right at the beginning, after maybe 100 random steps, the molecules are all still huddled together. The probability of finding any one molecule is packed into this sharp, narrow curve. They're very likely to be right near where they started.
But then you wait a bit longer, let's say 1,000 steps. The molecules have started to wander off. The curve spreads out, it gets wider and shorter. The uncertainty about where any single molecule is has gone up, but it's growing in this very specific, predictable shape. And after, say, 10,000 steps, you can see what's happened. The probability is spread out over a huge area. The molecules have diffused. We've watched a sharp spike of certainty melt away into a wide, flat wave of pure probability.
And this is where we get to the most mind-blowing insight of all. Because Feynman explains that probability isn't just a convenient tool for things we don't know. No, it's a deep, fundamental, unavoidable property of the universe itself.
Down at the quantum level, it turns out there's a cosmic trade-off built into the rules of reality. Nature basically says, you can know exactly where a particle is, but if you do, you cannot possibly know its exact velocity. Or you can know its exact velocity, but then you can't know its precise location. You can have one or the other. You can't have both. Period.
And this isn't because our measuring tools aren't good enough. It's a fundamental law of nature, spelled out by the Heisenberg uncertainty principle. What this equation tells us is that the universe has an inherent, built-in fuzziness. There's a hard limit to how precisely you can know things, and we can never, ever get past it.
You have to understand how completely shocking this idea was. It drove some of the greatest scientists nuts, including Albert Einstein. He famously complained about it, saying, God does not play dice with the universe. But here's the thing. Every experiment we've done since has shown that, yeah, at the deepest level, it really seems like he does.
So what does this actually look like? It means that our picture of an atom as a tiny solar system with electrons orbiting like little planets is just wrong. The reality is much weirder. It's a nucleus surrounded by a probability cloud. That electron isn't in any single place at all. It just exists as a cloud of chances, a region of space where it is likely to be.
So we've gone on this incredible journey, all the way from a simple coin toss to the very structure of matter itself. And it all leads us to this one, final, staggering thought. If the universe, at its very core, is truly a game of chance, then what does that say about the rules of the game that we are all playing?